Hey everyone, the rest of 8.7 is dedicated to polar graphs, which are kind of fun. You get some pretty cool graphs going depending on the equation. So they're all in polar coordinates. So when you look at the equations, you'll see r's and thetas, right? So all of these are the kind of different forms of equations that you'll see. And depending on the form, you'll get a certain type of graph. And a lot of times the graphs have names that are hard to pronounce. So the first type, we're going to look at circles and lemniscates. I always have a hard time pronouncing that one. So I did bring up a YouTube pronunciation.
Lemniscate. Lemniscate.
That's how you pronounce it.
Lemniscate.
Okay, lemniscate. Okay, so there you go. That's a professional pronouncing it. And those are like figure eights. That's an easier one for me to say. Figure eight. Okay, so this will kind of help you when you start to graph. You can look at the form and then you'll know the general idea of what it should be looking like. The next one are called
Limaçon. Limaçon.
limaçon. So that's that type where you have a plus or minus b sine theta, etc. Right? So if you see that form, then you'll know you have a limaçon. And then there is one special type when you see that a over b is equal to 1, or that means just a is equal to b. That one is actually has a name too. That's a cardioid. So in some of your homework, it'll ask you the name of the graph. And so this is a good reference page for that. And then the last one are roses. I can pronounce that. And the number of petals you see depends on that n. Right? So you have these forms, and then the n, if it's even, then you have twice the n number of leaves or petals. Leaves. Let's go with leaves. If n is odd, then it's just the same number of leaves as the n. Okay, so how are you going to graph these? There are some options for you. I'm going to show you a few. The most basic thing would just be to get out your calculator and plot some points and see what the graph looks like using polar graph paper. So let's look at some examples. We're going to try to graph each of the following and then identify the type of graph. So here we have 5 minus sine theta. I can make a little xy, r theta, not xy, r theta table. And then I'll go around the curve. Maybe I'll start with 0 degrees. So it's easiest if you pick the angle and then figure out the r. And then in your calculator, just make sure you're in degree mode and do 5 minus sine of 0, which turns out to be 5. Okay. And you don't have, I mean, you could go 15 and 30 and 45, but you might want to just skip a few for now, maybe do 45s and see where that gets you. And then if you need to fill in, you can do others, right? But now you can just do 5 minus sine 45, and then just get a decimal approximation. That's about 4.3. And then maybe go up to 90, right? You'll see that that's equal to 4. And then we can, start plotting some points. Oftentimes these are symmetric, so you can see the pattern symmetrically as you go, right? So we have 5, 0, which is right there, right? 1, 2, 3, 4, 5. 45, we got the 4.8, right? And then at 90 is the 4, right? So then probably at 135, I'll be back to that 4.8. And then over here at 180, back to 5. Okay, so I can start to see the shape of my graph form here. And if you check your completed notes, it'll look nicer. I'm just doing my best here. And then I would probably plug in 225 next to see what I get, right? 5 minus sine 225. I get 5.7, so it's going to go beyond that 5 out to almost 6, right? And then at 270, we do get 6. And then back to 315, back to 5.8, or 5.7, sorry. And then I'm back full circle. So eventually these will start to overlap or go back to where you started. Right? And there's my best graph I can do right now. Okay, so there's one approach, right? Is to make that table of values. Okay, so and then, you know, dot, 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 you can fill them in as you go. Once you get back to where you started, you know you're done. Okay. The other option, oh, and by the way, what type of graph is this? Let's see. Well, it has a minus there. So I'm scrolling all over the place, right? So I have a number, which I can think of as like A, and then I have like a plus or minus, it's a minus in this case. B is 1 sine theta. So that's that form, right? So I'm looking for something like that, which is here, right? So we've got that.
Limaçon.
Limaçon. Okay. Is it a cardioid? No, because the A and the B were not equal. It would be a cardioid if it were 5 minus 5 sine theta, like that. Okay. Now what I'll do is I'll show you a tech way to get this graph. Now you could use, if you have like a graphing calculator, you could try playing around with that to see the graphs that way. But even better is what's called Desmos.com. So I'm going to share my laptop real quick and show you, do a new share. So hopefully that comes up so you can see it. Oh, there's my pronunciation page. But if you type in Desmos, D-E-S-M-O-S, and then polar coordinates, right? I would probably just Google that, Desmos polar coordinates. It actually brings up a polar graphing calculator that's free. Like I haven't even signed up or signed in or anything, and I'm allowed to use it. And what I can do is just type in the equation right here. I don't worry about any of this stuff going down. That's actually how they generated all of the lines for the polar graph paper. Right? So like if I took off that r equals 1, it takes off that circle of radius 1. Okay, so then how do I get the equation in there? I could just type it in, 5 minus sine. Now theta is not on my keyboard, but there is this right here, show keypad. Is it there? Okay. A, B, C, there's a theta right there. Okay, and then I can now hide the keypad. And then there's the nicer version of the graph done using technology, looks better than my handwritten one. Okay, so you can rely on the graphing calculator. So now you have two ways you can plot points, just using your calculator and plotting them around the graph paper, or try the graphing calculator online. Either way works fine. If you think about just putting in some thetas, like if you put in 0 degrees, right, that would be 5 cosine of 0, and just plug that into your calculator. In degree mode, you'll see that you get 5. So when theta is 0, r is 5. So I already got a point right there. Is that 5 out? 1, 2, 3, yeah, 5. Okay. And then this one, because I'm multiplying theta by 3, it might be worth going to 15 degrees next. All right, so next I'm going to do 5 cosine of 3 times 15, which is 5 cosine 45. and then just get a decimal representation for that. Don't worry about using unit circle and exact values and all that. So that's 3.5 approximately. So at 15, I'm already down to about 3.5. Okay. And then if I do 30 degrees, that's going to be 5 cosine 3 times 30. That's 5 cosine 90. And then cosine of 90 is 0. This is equal to 0. So then I'm at the origin, right? So this one's starting like this, right? And then if I just keep on going, I'm going to do 60 degrees, 75, 90, plug them in and see what happens. Now, what am I expecting to see? That gets to the form of this equation. If I go look at some of the different equations, is there anything that looks like that? A number cosine times a value in front of theta. Well, here they are, right? But mine is the cosine version. And n is actually odd in this case, right? So there is one where n is 3, and I'm in my case. So I should expect to see that. Right? 3 leaves. In that sort of pattern, okay? So, knowing what to expect is going to help you when you start plotting those points out. So let's then cut to the chase, and we can see what the graphing calculator does. So we'll go back there. Thanks for being patient with me as I go all over the place here. Okay, so what I'm typing in is 5 cosine. So I gotta get rid of that negative and then put in the 3. And it just does not, oh, and it's cosine, right? There's the sine one, also 3 petals, but sort of in a different area of the graph. There's 5 cosine theta. So we were on our way to getting that, right? But now I've got it, and then I can, when you do these online, there's no graphing tool in my math lab, so it'll be a lot of multiple choice. So check out my completed notes for the completed version. I did draw that one as nice as I could on the handout, but that's what it looks like. Okay. Let's try a couple more, and we'll just now stick with Desmos. If you want to try the plotting of the points too, that's good. Right. So that was number 9. That's a rose with 3 petals or leaves. How about number 10? It's 3 plus 2 cosine theta. Well, let's see what it looks like. So it's 3 plus 2 cosine theta from the handout. And it looks like that. Right. That's the really bad.
Limaçon.
Limaçon. It's French. Limaçon. So that's a limaçon. That looks pretty cool. Okay, so we got that one, and then the final one. Okay, so let's put that one in now. These have to be R equals. As far as I know, I've been playing around with this for not too long, so I'm not an expert by any means, but I've played around with it. I need R equals, not R squared. So instead of R squared equals 9 sine 2 theta, I'm going to put in R equals, there's a square root here, square root 9 sine 2, and then where's my theta? Okay, and then that's what it looks like. Now I got to be a little bit careful because it could be a negative 9 sine 2 theta 2. So if I put a negative in there, well, it turns out that's the same thing. So those are identical, plus or minus, but it is technically plus or minus the square root. But I check them both and they're the same. So that's good. Okay. Okay, so let's jump back to the handout. We got one more example. But it's kind of fun to play around with. You can do all sorts. I mean, if you want to start exploring some pretty crazy looking graphs, you can get like even if you Google like Desmos polar like butterfly, I think there's like a butterfly. Yeah. Butterfly. Ooh, look, see, that's kind of neat. So that's how polar graph. I mean, the graph gets pretty complicated, right? But using polar coordinates, oh, there's the polar coordinate version right there, right? You can generate some pretty cool stuff. Anyway, okay, let's get back to the handout. So again, you know, check out the completed notes if you want to see the nice graphs that I drew, but I won't bother you with me trying to do it right now. Okay, how about this one? So this one says convert to rectangular form first, and then graph the result. Okay, so how can I do that? This is going to go back to using those little equations from page back to where are they? These. You want to use those for this problem. Okay. In particular, I think the one that comes into play here will be this one and this one. So let's see how that will work out. Okay. So the first thing I'm going to do on this problem, which you might wonder why, and I'll tell you why in a second, but I'm going to multiply both sides by r. So this gives me r squared equals, and then I'm going to put the r between the 4 and the sine theta because it's all multiplication. So that's okay to do. And the reason now is I have this r sine theta, which I know from that formula above is equal to y. Also from that formula above, I had r is equal to the square root of x squared plus y squared, right? If I square both sides, r squared is equal to x squared plus y squared. It's just Pythagorean theorem. So I'm going to do those two substitutions. I'm going to substitute this one and this one. R squared, I'm replacing with x squared plus y squared. R sine theta, I'm replacing with y. And there you have it. There's your equation in rectangular form. Now there's some different, now this gets into just algebra, right? If I just add the 4y to the other side, this might be familiar to some of you. Okay. I wanted to get this graphed. I would complete the square. Do you remember doing that? Or if you're in 372 at the same time, you've probably done that this semester. But what I'm going to do is take half of the 4, which is a 2, and square it, which is 4. So I'm going to add 4 to both sides. Right? And then this is a perfect square that factors. It factors into y plus 2 squared. Right? So this is that form of a circle and rectangular form that you can now graph. Right? It has a radius of 2, the square root of that number, and a center of 0, because there's no number within the being added or subtracted to the x, -2, the opposite of that 2, right? So this would be center 0, -2, radius of 2. So it'd go up to there, over there, there, and there. It'd be this little circle down here. Okay. And that's it. So I did that one in rectangular form. You would get the same graph if you did it in polar form, just using that version. Right? It's a circle. If you plugged in thetas and r's and then plotted it on polar graph paper, it would end up in that same location, the same size, and all that. So just the whole point of that problem is the comparison of rectangular and polar. Sometimes rectangular is easier, sometimes polar is easier. It's kind of nice to have both tools to get the graph you're looking for. Forgot that parenthesis. Okay, hope that wasn't too all over the place. Let me know if you have any questions or if you need any more clarification, and I hope all's well. Talk to you later.